In this presentation, I'm going to explain control rectifier for DC motor drives. This is the second part of DC drive, and in this one, by using control rectifier, you can control the speed of DC motor drives. Control rectifier for DC motor drives. Control rectifiers are used to get variable DC voltage from AC source of fixed voltage. And control rectifiers can be classified into single phase fully controlled rectifier, single phase half control rectifier, three phase fully controlled rectifier, and three phase half control rectifier. And fully controlled rectifiers can be operated in two quadrants, that is in first quadrant and fourth quadrant, whereas half control rectifiers can be operated in only one quadrant, only first quadrant it can be operated. And control rectifiers for DC drives are widely used in applications requiring wide range of speed control and or frequent starting, braking, and reversing. And some prominent applications are rolling mills, in paper mills, printing presses, mine winders, and machine tools, etc. And that is in fully controlled rectifiers, the average output voltage is in a single phase, it is equal to 2 Vm by pi cos alpha. In three phase, it is equal to 3 VML divided by pi cos alpha. In these two cases, if you are running the making the firing angle less than pi by 2, output voltage will be positive. And if alpha is more than pi by 2, it will be negative. But in other two cases, half control case, you can get only a positive voltage, whether you are changing the firing angle from 0 to pi. Single phase and three phase control rectifier circuits are shown here. This is a single phase fully controlled rectifier for DC motor, separately excited DC motor. It can be operated in either in first quadrant or in a fourth quadrant. Therefore, by controlling the firing angle of these thyristors, if alpha is less than pi by 2, 90 degree, output voltage will be positive. It can be operated in the first quadrant. If alpha is made more than 90 degree, the output voltage will become negative and it can be operated in the fourth quadrant. But in the case of a half control, single phase half control rectifier for DC motor, in that case, you are replacing the diode. These SCRs are replaced by these diodes here. And in this case, the output voltage equation is equal to Vm by pi into 1 plus cos alpha. That is, if you are changing the alpha from 0 to pi, always the magnitude of VA will be positive, or always you will be getting a positive voltage across the armature. Therefore, it can be operated only in the first quadrant. Similarly, in three phase also, in three phase fully controlled rectifier, 3 VML by pi cos alpha, by changing the alpha, you can made to work in either in first quadrant or fourth quadrant. Here also, it can be in half control, three phase control rectifier for DC motor, it can be operated only in the first quadrant. Okay. Considering single phase fully controlled rectifier for DC motor separately excited, this is the motor, this separately excited DC motor that is fed by a control rectifier, single phase control rectifier. There are four thyristors, T1, T2, T3, T4 they are used. And the equivalent circuit of the separately excited DC motor, armature resistance RA, armature inductance LA, back EMF E. So this is the equivalent circuit of the motor that is fed by a single phase fully controlled rectifier. And when in this case, when the armature current does not flow continuously, then the motor is said to be in operating in discontinuous conduction mode. When the current flows through is continuous, then the conduction is said to be continuous. Therefore, discontinuous conduction mode means armature current is not continuous. There will be zero current duration, and continuous current mode means always the current will be more than zero. Therefore, the two modes of operation are there. This is showing a continuous conduction mode in which you can see that one always the current is more than zero. You are getting a current through the armature, and this is the current at the source side. Therefore, the source side is an AC current, and that is here always the current through the motor is always more than zero. It's a continuous conduction. And during the alpha to pi plus alpha, here T1 and T2 are conducting, and when pi plus alpha to 2 pi plus alpha, T3 and T4 are conducting. Continuing the single phase fully controlled rectifier fed separately XDC motor. In continuous conduction, this is showing the continuous conduction mode. In this one, current is continuous, and here from omega t equal to alpha to pi plus alpha, thyristors T1 and T2 are conducting, and the armature voltage VA is same as the source voltage VS, and the source current IA is same as the load current, that is from alpha to pi plus alpha. At omega t equal to pi plus alpha, at this instant, T3 and T4 are turned on. We are turning on T3 and T4 and turned on, and T3 and T4 and T1 and T3 and T4 are turned on. T3 and T4 are T1 and T2 are turned off automatically by the reverse voltage applied due to the turning on of T3 and T4. When T3 and T4 are turned on, a negative voltage comes across the SCRs which are already in conduction, T1 and T2, that will be getting turned off. And during omega t equal to pi plus alpha to 2 pi plus alpha, armature voltage VA equal to minus VS. Therefore, that is from this instant to this instant is equal to minus VS, and the armature current, armature here, the source current will be equal to minus IA. Therefore, that is the in continuous conduction mode. Here, the average armature voltage is given by VA equal to 1 by pi integral alpha to pi plus alpha Vm sin omega t, or it is equal to 2 Vm by pi cos alpha. In this case, if alpha is less than pi by 2, you will be getting a positive voltage here. If alpha is more than pi by 2, you will be getting a negative voltage across the armature. Now, in continuous conduction mode, average armature voltage VA is given by 2 Vm by pi cos alpha, and when alpha is less than 90 degree, average armature voltage is positive, and when alpha is more than 90 degree, armature voltage is negative. And in the case of, let us see the discontinuous conduction case. In discontinuous conduction case, as shown here, there will be certain instant during which the armature current equal to 0. The current is not continuous. During that period, the voltage will be equal to the back EMF, but the voltage across armature will become equal to back EMF. Therefore, here from omega t alpha to beta, that is from omega t alpha to beta, thyristors T1 and T2 are conducting, and the armature voltage VA is same as the source voltage. Armature voltage is same as the source voltage from alpha to beta. Same source voltage VS, and the source current is same as the load current. And at omega t equal to beta, armature current IA decreases to 0, and T1 and T2 are turned off. At this instant, we can see that one current has gone to 0, and the thyristors T1 and T2 are getting turned off since the and the anode current is to 0. Now, hence, during beta to pi plus alpha, during that event, all the devices are getting turned off. T1 is turned, T1, T2, T3, T4, all are getting turned off. Since the armature current is 0, the armature voltage is same as the back EMF. Therefore, during this period, here, during this period, the voltage across the armature is same as the back EMF, because none of the thyristors are conducting, and since motor is running, there will be back EMF. That will be the voltage that is coming across the armature. That is from beta to pi plus alpha. Continuing discontinuous conduction mode of single phase fully controlled rectifier. Here, this is the diagram showing the voltages, currents, and the source current, and the thyristors which are conducting. During this period, T1 and T2 are conducting. Certain period, none of the thyristors are conducting. Next period, T3 and T4 are conducting. During omega t equal to beta to pi plus alpha, all the devices are off, since the armature current is 0 and the armature voltage is same as the back EMF. That's already I told, this is the same as back EMF. At omega t equal to pi plus alpha, T3 and T4 are pi plus alpha, T3 and T4 are getting turned on, and the armature voltage now VA equal to minus VS, and the source current Is equal to minus Ia. That is what is at this instant. This is at this instant, the armature voltage is equal to minus Vs at this pi plus alpha. In this case, the thyristors T3 and T4 are getting turned on. Since the armature current Ia is not perfect DC, can say that it is not perfectly DC, the motor torque will be fluctuating. Though the torque fluctuates at a frequency of twice the frequency of this one, that is 100 Hertz, due to the motor inertia, it is able to filter out these fluctuations, giving nearly a constant speed and ripple less back EMF. That is why we can say that back EMF is a constant. That is because of, even though current has got a ripple and the torque has got a ripple here, because of the inertia of this motor, the speed is constant and the back EMF is a constant. Continuing discontinuous conduction mode of operation, average armature voltage is equal to Va equal to 1 pi integral alpha to beta Vm sin omega t d omega t plus integral beta to pi plus alpha back EMF voltage is there E d omega t, and you will be getting this is the average voltage that is coming Vm into 1 plus cos alpha plus E into pi plus alpha minus beta divided by pi. This is the average voltage coming across the armature in the case of discontinuous conduction mode. And torque is equal to T equal to K into Ia, and back EMF equal to E equal to another constant K into omega m. Since omega m equal to E by K, from this one E by K, which is equal to Va minus Ia Ra divided by K, substituting for this Va from this equation, you will be getting Vm into 1 plus cos alpha plus E into pi plus alpha minus beta divided by pi k minus Ra by k square into T. That is the equation for the speed versus torque of a during the discontinuous conduction mode. And here omega m equation, omega m, we are substituting this equation here, and omega m equal to Vm into 1 plus cos alpha plus K into omega m into pi plus alpha minus beta divided by pi k minus Ra by k square into T. And substituting this equation here, you'll be getting the final equation for the omega m speed. It is equal to Vm into 1 plus cos alpha divided by K into beta minus alpha minus pi into Ra divided by k square into beta minus alpha into T. This is the equation for the speed of a motor which is operating in a discontinuous conduction mode, the speed versus torque equation. Continuing the discontinuous conduction mode of operation here, so this is the voltage plot and this is the current through the armature. This is discontinuity is there, and we are seeing here the omega m equation equal to Vm into 1 plus cos alpha divided by K into beta minus alpha minus pi into Ra divided by K square into beta minus alpha into T. This is the case of in a discontinuous case. Therefore, here the most important thing is what is beta. We don't know the beta value. Beta value depends upon the inductance value, different parameters that decide beta. Therefore, we don't know what is the discontinuity, how much it is there. Therefore, to find out the beta, there is a certain procedure is done. Here, first one, during this period, that is omega t between alpha and beta, what is the equation for the current through the motor? Therefore, it is equal to, as you know that one, the voltage Va equal to La dia by dt plus Ra into Ia plus back EMF, that is equal to Vm sin omega t. That is represented as equation 1. Then for omega t between beta and pi plus alpha, as you know that one, during this period, Ia equal to 0. Ia equal to 0. At the same time, the voltage across the armature is equal to the back EMF. Therefore, these are the two equations that is governing the current through the armature during these two intervals. Now, let us see the solution of the first equation. The solution of the first equation is given by Ia into Ia omega t is given by Vm by Z sin omega t minus phi minus E by Ra plus K1 into e raised to minus Ra t divided by La. That is between omega t alpha and beta. where Z is equal to the impedance root of Ra square plus omega La square, and phi is equal to the factor angle, which is tan inverse omega La divided by Ra, and the time constant tau A is defined as La divided by Ra. And to find out this constant, you have to find out what is this constant. To find out this constant, at omega t equal to alpha, that is at this instant, as you see that at this instant, omega t equal to alpha, Ia alpha equal to 0, the current equal to 0. Substituting this one in the equation 1, here you are going to substituting the equation 1, substituting that one in this equation, you will be getting what is the value of the K1. You are going to substitute that one, and in that, from that equation, the only unknown is the K1, and that K1 is equal to E by Ra minus Vm divided by Z into sine alpha minus phi into e raised to Ra divided by omega La into alpha. That is Ra alpha divided by omega La. This is the value of the constant K1. Continuing this discontinuous conduction mode of operation, in order to find out the value of the beta, we have already in the last slide I explained how can you find out the constant K1, and substituting this value of the K1 in that equation, that is Ia omega t, you are substituting Vm by Z into sine omega t minus phi minus E by Ra plus E by Ra minus Vm by Z sine alpha minus phi into e raised to Ra alpha divided by omega La and e raised to Ra divided by La into t. So this is the equation after substituting the value of K in this one. Now Ia omega t equal to Vm by Z sin omega t minus phi minus E by Ra plus E by Ra minus Vm by Z sin alpha minus phi, then e raised to minus omega t minus alpha into cot phi, minus alpha into cot phi. This is the equation for armature current in between alpha and beta. Now to find out beta, as you know that one, as omega t equal to beta, that is Ia beta, that is equal to 0. Substitute this, instead of omega t in this equation, you substitute beta and equate to 0. That is, you are substituting for this omega t here, that is omega t substituted by beta, and you are finding out the value of beta from this equation after equating to 0 this one. Therefore, solving this equation, two equation, you can find out what is the beta, that is the conduction angle can be found out. Now at boundary between continuous and discontinuous conduction, boundary in the sense just changing from discontinuous conduction to continuous conduction mode, that's called a boundary. In that boundary, beta will be equal to pi plus alpha. Continuing discontinuous conduction mode, there is a speed what is called the critical speed. The critical speed is the speed corresponding to this particular border, which is changing from continuous to discontinuous conduction. Therefore, at boundary condition between continuous and discontinuous conduction, beta is equal to pi plus alpha. Substituting the beta equal to pi plus alpha in this equation, because already we have derived it is equal to Vm by Z sine beta minus phi minus E by Ra plus E by Ra minus Vm by Z sine alpha minus phi into e raised to beta minus alpha into cot phi, that is equal to 0. Now you are replacing this beta by pi plus alpha here. That is the boundary condition. That is changing from discontinuous to continuous conduction. Substituting beta pi plus alpha in this equation, and from that equation you will be getting it is equal to, reducing this equation, you will be getting E by Ra equal to Vm by Z sine alpha minus phi into 1 plus e raised to minus pi cot phi divided by e raised to minus pi cot phi minus 1. And from this equation you can find out what is the omega mc, that is omega mc is the critical speed at the boundary of the continuous and discontinuous conduction. And omega mc is given by, from this one, omega mc is equal to, it is Vm by Vm Ra divided by K into Z sine alpha minus phi into 1 plus e raised to minus pi cot phi divided by e raised to minus pi cot phi minus 1. If motor speed is more than the critical speed omega mc, it will operate in a discontinuous conduction mode. Therefore, to work it in continuous conduction mode, the motor speed should be less than the critical speed omega mc, which is given by this equation. Coming back to continuous conduction method, average voltage across the armature already we derived. It is equal to 2 Vm by pi cos alpha. Torque equation T equal to K into I equal to back EMF K into omega, and substituting that one, omega m equal to E by K or VA minus IARA divided by K, or 2 Vm by pi cos alpha, 2 Vm by pi K cos alpha minus Ra by K square into T. Therefore, this is the speed torque relation in the case of continuous conduction mode. For in continuous conduction mode, this is the region in which it is obeying this rule omega m, and T is obeying this equation. Therefore, this is the continuous conduction operation already I explained. This is the current and this is the source current, and these are the thyristors T1 and T2 in during this period, and during this period T3 and T4, and that is continuous. This is the continuous conduction mode, and this is the discontinuous conduction mode. Now let us see that in discontinuous conduction mode, what is the speed corresponding to zero torque or starting omega m0. That's a function of the alpha. As alpha changes, this value will be changing. Therefore, this is representing speed torque characteristics of a separate single phase fully controlled rectifier fed separately excited DC motor. This is in discontinuous conduction mode, and this is in continuous conduction mode. Therefore, this is representing speed torque characteristics of a single phase fully controlled rectifier fed separately excited DC motor. And no load operation is obtained. That is, we have to find out what is this speeds corresponding to no load torque. Therefore, the no load operation is obtained when the load current equal to 0. When both, that is, load current equal to 0 means both thyristor coils T1 and T2 and T3, T4 are fails to fire. At that period, the IA will become equal to 0. That will happen when back EMF is more than V, that is Vs. That is, if E is more than Vs, it will be happening throughout the period for which the firing pulses are present. When alpha is less than pi by 2, that is, firing angle is less than pi by 2, E should be greater than or equal to Vm. And when alpha is more than pi by 2, E should be greater than or equal to Vm sin omega t. This is the condition to get to decide the starting speed here. Therefore, omega m0, that is the speed corresponding to zero torque. Omega m0 equal to Vm by K for alpha between 0 and pi by 2. That is for 0, 60 degree and pi. During that period, the starting is decided by Vm by K. And when alpha is between pi by 2 to pi, that is for this one, this starting point, that is decided by Vm sin alpha divided by K. Now, in discontinuous conduction, that is, this is a discontinuous conduction region. In discontinuous conduction, any increase in torque and accompanied increase in IA causes beta to increase, that is, conduction angle increases, and VA to drop, that is, average output voltage gets dropped, leading to drop in the speed in a very large, that is omega, that suddenly speed is reducing. As torque increases, speed is getting reduced suddenly in the discontinuous conduction region. Therefore, in continuous conduction mode, average voltage is given by 2 Vm by pi cos alpha. Therefore, when alpha is less than pi by 2, you will be getting a positive voltage, and the maximum when corresponding to alpha equal to 2 Vm by pi. When alpha is more than pi by 2, you will be getting a negative voltage, maximum equal to minus 2 Vm by pi cos alpha. Therefore, you can have a positive voltage and negative voltage. When it is positive voltage, it will be working in the first quadrant. When it is negative voltage, it will be working in the fourth quadrant. And here, correspondingly, as corresponding to 2 Vm by pi cos alpha, omega m is given by 2Vm by pi cos alpha, 2m by divided by k, 2Vm cos alpha divided by k minus Ra by k square into t. Now this is corresponding to the first quadrant operation in which alpha is less than 90 degree. Here you can see that one omega m is more than, or that is positive, or it is equal in clockwise direction. The torque that will be rotating in a clockwise direction. Back EMF with a plus here, minus here. The voltage, armature voltage plus here, minus here. This is called forward motoring region, and that is what is happening in the first quadrant. Now, if alpha is more than 90 degree, here what happens is that polarity gets output voltage polarity reverses, back EMF polarity reverses, and the rotation that is also reverses in the anti-clockwise direction, and that is working in a regenerative braking mode. That is, it is called reverse regenerating mode. That is, when alpha is more than pi by 2, when alpha is less than pi by 2, it is working in a forward motoring region. Now let us see a problem. A 200 volt, 875 rpm, 150 amperes separately excited DC motor has an armature resistance of 0.06 ohms and is fed from a single phase fully controlled rectifier with an AC source voltage of 220 volt 50 Hz. Assuming continuous conduction, calculate firing angle for rated motor torque and 750 rpm. Then second, firing angle for rated motor torque and minus 500 rpm. Third one, motor speed corresponding to alpha equal to 160 degree minus equal to 160 degree and rated torque. Now solution. At rated condition, the rated condition means 200 volt, 875 rpm and 150 amperes. In that condition, the back EMF is given by V minus IARA for 200 minus 150 into 0.06. It is equal to 191 volts. This is the back EMF corresponding to 875 rpm. Therefore, the back EMF corresponding to 750 rpm, that can be calculated 750 divided by 875 into 191, or this is equal to 163.7 volts. That is the back EMF corresponding to the speed that is corresponding 750 rpm. Now, once you get the back EMF, you can calculate what is the armature voltage, what is the required armature voltage, which is equal to E plus into IARA. That is 163.7 plus IA is same because the rated torque is, torque is rated value for 150 into 0.06 or 172.7 volt is the voltage that is required across the armature. To get this much voltage, what should be the firing angle? VA equal to 2Vm by pi cos alpha. From this equation, substituting for V this one, you will be getting what is the firing angle alpha equal to 29.3 degree. Second part of the question is the speed is reduced, it is a minus 500 rpm. Now corresponding to minus 500 rpm, you have to calculate what is the back EMF. And minus 500 rpm, the back EMF corresponding to that one, you can calculate. That is equal to minus 109 volts. And from that one, you can calculate what is the armature voltage required. V equal to E plus IARA. And then you will be getting what this is the voltage that is under voltage, the voltage that is across the armature. And correspond to get this much voltage, you have to calculate what is the firing angle alpha. From this equation, you can substitute that one. You can get the firing angle alpha is equal to 120 degree. Now the third part of the question is that corresponding to a firing angle of 160, what is the speed of that one? Therefore, corresponding to alpha 160, you have to calculate what is the armature voltage. That is calculated. And substituting this armature voltage in this equation, you can find out what is the back EMF equal to VA minus IARA. You are calculating that is equal to 186 minus 150 into 0.06 or 195 volt is the back EMF. Then corresponding to this back EMF, you have to calculate what is the speed, and then you will be getting it is equal to 893.2 rpm.